Hello, so this is my student project presentation on the parallel computation of the n-body problem. My name is Ryan Sim. So my project is about the n-body problem. This is a generalized term for where you have a system of many bodies, anywhere from two to thousands of bodies, and how they interact with each other due to the forces that are inherent in them. So can be anything from gravitational forces to Coulomb forces, and this has effects in the modeling of, say, galaxies as well as the modeling of fluids. What I looked at is different computational algorithms. So the Barnett algorithm is a type of parallel algorithm, but single node algorithms are basically computational algorithms that run on one computer, and this scales in n squared. So it scales with it scales with the square of each body. The Barnett algorithm is much more efficient in that it scales in n log 2 of n, and parallel computation can range from anything from just a slight improvement to anywhere to just O of n. The speedups are extremely fast. So the graph on the right basically shows for just a parallel computation, but the Barnett algorithm actually, in my case, sped up for 15,000 particles in less than a couple minutes. So this is just an extension of what different types of algorithms look like. So the one on the right is just a single node computational algorithm. And so you see that it's basically two nested for loops, and that's why it's n squared. And so for each body, you're seeing how the forces interact with each other body. And so then you compute the velocities and update the positions, and etc. The Barnett algorithm is actually much more it's different in that it breaks up the space into quadrants, and then it breaks up each quadrant into more quadrants, and then you're basically computing the center of mass to see how each particle reacts with each center of mass, and you have basically a node which you can work towards upwards to find that kind of calculation and distribute it much more efficiently. So I just want to show you how to run it on the CARC, which was basically the it's basically the oops, sorry. It's basically the HPC at USC, and because I work there, I was interested in this topic, and this is why I was working on this topic. So if you look at, so this is basically my program. As you can see, it has the n as well as the bounds defined, and basically this is the code that links the specifications that you have to OpenMPI. And so you basically have to do something called module purge and then module load Intel, module load OpenMPI. And basically what this does, it gets rid of all the dependencies. So you have to define which compiler you want it to run on, or which processor you want it to run on. You define all the packages that you want, and that just does it in a very simple, easy way. And then what you do after that is you compile it with MPICXX with output.x, so that's the output file name, and then the file that you want to compile. And so you get output.x. And so what you do then is you basically specify that you want to get the modules, and then basically run using MPI run the compiled file that you have. And so how you would submit the job would be like this. And then once you have it submitted, you can check basically on the status of the jobs. SQ basically looks at all the jobs. And for example, this is a certain process that was submitted, and then I'm guessing that it has to do with MATLAB. So that's just very simply how to run it on CRC. Very easy. And the reason I chose it again is because there was a wealth of information in my coworkers, and because I was interested in seeing how the things that I was learning could be applied. So these are just some visualization examples. This is for a galaxy, but also if you want to take a look, let's see. So this is just showing the circular orbit for our planets, and the n is basically n is 5, so there's 5 bodies, and they're kind of interacting with each other due to gravitational forces. And then lastly, what I learned about parallel computation and how it's applied, as well as basically the field of the n-body problem and kind of the approaches that are taken, as well as a lot of um, the tools that I need to kind of apply scientific research to scientific computation. And so the paths that I wanted to go down initially were looking at these things called non-collision singularities. So the Pine-Lev conjecture basically says there are non-collision singularities for n greater than 4. And so in this five-body system, you see this middle particle is basically going up to infinity without, and a singularity is where a particle collides or basically doesn't interact with other particles at all. And so this particle doesn't interact with the other particles directly, but it goes off to infinity. That's my student project on parallel computation of the n-body problem. Thank you.